Morning, Aussie. I've got some salt, chemical name sodium chloride. This is water, quite pure water. I put some sodium chloride, some salt into the water and shake it around. I'm going to talk to you about the concept of chemical species and of speciation. And this is perhaps the most important discussion we will have in all of our time together in this unit. So shake it up. What's in the container, Aussie? Huh? Well, if that was water and that was salt, then there's water and salt in the container. Aussie, I can't see any salt. Can you? Aha! We've talked about this before, haven't we? Okay, so there is no salt there. Water molecules are sort of able to compete and grab the sodium ions and the chloride ions and separate them from each other, and they're now spread out amongst the water molecules. So in there are sodium ions and chloride ions and water molecules. Well, you're on the right track. First thing, yes, there is no sodium chloride in there. Sodium chloride's a white crystalline solid, and there is none of that. But it's inconceivable that the charged ions, sodium ions and chloride ions, can be in there as some independent species floating around on their own. If there was enough attraction between polar water molecules and sodium ions, and the water molecules and chloride ions, to pull them apart from the attractions between sodium ions in the crystal, then surely there's enough of that attraction there for the water molecules to be still hanging on to the sodium ions and the chloride ions. So what we believe is that the sodium ions are surrounded by a shell of sodium ions and a shell of water molecules, and the chloride ions are surrounded by a shell of water molecules, and we call those aquated or hydrated ions. So the sodium ions, each one of them, we imagine to be surrounded by water molecules with the negative end of the waters pointing towards the sodiums, and the chloride ions with the positive ends of the water molecules pointing towards them. This is the way we write that, is aquated, or a lot of people use the term hydrated sodium ions, and this is this aquated chloride ion produced from sodium chloride in the solid in the presence of water. So these aquated sodium ions and aquated chloride ions are said to be the species that are present in this solution, apart from the water molecules. Species, any atoms or collection of atoms, molecules, ions, whatever, charged or uncharged, that are believed to exist, that do exist for some finite time. These entities are called species. In solution, if we dissolve a 0.1 molar solution of sodium chloride, if we dissolve 0.1 of a mole of sodium chloride into water, there are 550 molecules of water for every sodium ion and every chloride ion. So the sodium ions and chloride ions are a long way apart from each other. They don't even know that each exists. Miles apart from each other. They're existing with the water molecule shell around them as independent species. Okay? Okay then. Now, copper sulfate. We saw that in the lab yesterday. You know it's blue, dissolve it in water, it makes a blue solution. What species are present? Copper sulfate. Can I use this, Prof? Copper sulfate, let me start again. CuSO4. So I'd say in solution there's copper 2+ ions and sulfate 2 minus ions. Okay? Oh, hang on. Sorry, Prof. There would be copper 2 plus ions surrounded by a shell of water molecules, aquated copper ions, and aquated sulfate ions and water molecules. Okay, that's good. And what gives a copper sulfate solution its blue colour? What brings about the blue colour of a copper sulfate solution? Well, we know that water is colourless, so if the solution is blue, it must be due to one of the species, at least one of the species that's in there, so it's either aquated copper ions or aquated sulfate ions. How would I know? Let me give you a clue. Solutions of sodium sulfate in water are colourless. We're talking about copper sulfate, and I'm telling you that solutions of sodium sulfate, potassium sulfate are colourless. Okay, so if a solution of sodium sulfate is colourless, the sulfate, the aquated sulfate ions, let me start again, Prof. The aquated sulfate ions floating around aren't causing the solution to be blue. They're not having any effect on the colour, on the colourlessness. So the blue colour of copper sulfate solutions must be due to aquated copper ions, that species. Good. Let me turn to solutions of barium chloride. It's a solid, put it into water, and we have barium 2 plus ions and twice as many aquated chloride ions. Now, if we put a solution containing sulfate ions, so sodium sulfate, into this solution, we get a white precipitate of barium sulfate. You've seen that. Okay? What is it that reacts with the sulfate ions to produce barium sulfate precipitate? Well, that'd be the barium chloride that's in the solution. Okay, sorry, there is no barium chloride in the solution. The barium sulfate precipitate must come from either the aquated barium ions or the aquated chloride ions. Since we're forming barium sulfate, it must be the aquated barium ions, which are the species that react with sulfate ions to produce barium sulfate. Excellent. The reactant species is aquated barium ions, and they react with the aquated sulfate ions to form barium sulfate solid. A lot of textbooks you'll find will give a chemical equation like this. Barium chloride, often aqueous, and sulfate ions give barium sulfate and some chloride ions left over. But that really is misleading because there is no such thing as barium chloride in a solution of barium chloride. Okay? Now also, if we add a solution containing silver ions to a solution of barium chloride, I should have perhaps made the point here that this is a solution with no barium chloride as such in it, although we put barium chloride in there. If we add some silver nitrate to this solution, then the silver ions in the silver nitrate solution, aquated, produce another precipitate, a different precipitate of silver chloride. In this case, the aquated chloride ions are the reactant. So a solution of barium chloride contains two independent reactant species, aquated barium ions, which can do their thing, and aquated chloride ions, which can do their thing, more or less independently of each other. Okay? Move on. We bubble hydrogen chloride gas into water and we produce what's called hydrochloric acid, which is a solution of hydrogen chloride. What about the species in there? Piece of cake, Prof. There are no HCl molecules in that solution. There are only aquated hydrogen ions and aquated chloride ions. Pretty sure about that. Good. Good, Ozzy. And we would write that as HCl forms H plus aquated ions and Cl minus aquated ions. Okay. What about a solution that contains acetic acid or ethanoic acid in water? Species in that solution? Same deal, Prof. There'd be aquated acetate ions and aquated hydrogen ions. I know all about acids. They break off and the hydrogen ions form aquated hydrogen ions. Maybe I led you down the wrong path a little bit, Ozzy. It's true that this is an acid, but it's one of those things called a weak acid, and instead of saying that it splits up entirely into acetate ions and hydrogen ions, it forms what we call an equilibrium. Only some of these split up to form acetate, aquated ions and aquated hydrogen ions. In fact, in about a 0.1 molar solution, only about 1% there is that. The 99% is this. So the species in solution are, apart from water molecules, mainly aquated acetic acid molecules, and to a lesser degree, acetate ions or ethanoate ions and aquated hydrogen ions. Okay, all right. Now that's when we just put some acetic acid into water. Now if we add some sodium hydroxide solution, so we're changing the concentration of hydroxide ions from an external source, we can change the relative amounts of this species compared to that species. And not sure where you're at in your chemistry yet, but if we add sodium hydroxide ions, a solution containing hydroxide ions, we convert some of that to that because the hydroxide ions grab the hydrogen ions to form water. So the more sodium hydroxide we add, the higher the concentration of acetate ions and the lower the concentration of acetic acid. And I can actually plot something like pH 2, 3, 4, 5, 6, 7, 8. And here the percentage of all the stuff that is present as either acetic acid or acetate ion. At this pH, it's all present as acetic acid. As I make the solution more basic by adding more hydroxide ions, this goes down and the concentration of another species, acetate ions, goes up. And they become 50-50 at about a pH of 4.8. 50-50, this keeps going down, this one keeps going up. This change in the relative amounts of this species compared to this species, due to the external factor of adding hydroxide ions, is called speciation. What species exist? How is the distribution between them changing according to whatever we do? Well, why is there a 50-50 percentage? That means equal concentrations, doesn't it, of acetic acid and, can I borrow this, Prof? And acetate ions, aquated, of course. Sorry, Prof, I'm not meaning to correct you, just clarifying in my own mind. Why are the concentrations equal at 4.5 or whatever it was you said? Why not 3 or 7? Ozzy, we'll get into some quantitative calculations later in this course. It depends upon the notion of chemical equilibrium and the values of equilibrium constants. For now, try to accept the fact that the speciation concept, changing different amounts, redistributions between species as we do something to it. Now, one last example, extraordinarily important in today's world, in the sense of increasing concentration of carbon dioxide in the atmosphere, which is happening. The data is quite strongly that over the last 200 years, the concentration of carbon dioxide in the atmosphere is going up. If we dissolve carbon dioxide in water, like for example in the surface layers of seawater, the carbon dioxide forms and water forms carbonic acid, which is a weak acid, and there are lesser amounts of the hydrogen carbonate ion, and even lesser amounts again in equilibrium of carbonate ions. This is one of the most important systems in our Earth today. Now, if the pH of the solution changes, if we increase the concentration of hydroxide ions, that means we increase the pH. We change the relative amounts of all three of these species. Again, I happen to have this is a very, very important graph. At low pH, high acidic conditions, almost all of the carbonate is present as carbonic acid. As we increase the amount of sodium hydroxide, increase the pH, concentration of carbonic acid goes down and the concentration of hydrogen carbonate comes up as we convert some of this into this. This crossover is at about pH 6.4. As we increase the pH further and further and further, this one goes to almost nothing. This one reaches a peak of almost 100% of it is this species, and then it starts to go down again as this is hydrogen carbonate ion, aquated, is converted into the aquated carbonate ions. So their concentration goes up and these go down, and they're equal at about pH 10.3. So depending upon the pH, so depends the relative amounts and the relative concentrations of these three different species. Another example, and a hugely important example, of speciation. Now, one last example. Last example. If you were to ingest in a drink or in some food some arsenic, we all know arsenic, throw up our hands, horror, murder stories, intrigue. If you were to ingest some of this stuff by dissolving it in a drink, your life would be in serious jeopardy. It takes a surprising amount, but not a huge amount, to something like a gram, I think, and you're gone. Do you know that lobsters are very rich in arsenic in the flesh? That luxury seafood item, lobsters, really quite a lot of arsenic in them. A couple of days ago I had, I'm dreaming, 10 lobsters for lunch, and I survived pretty well. And they contain a lot of arsenic. And the reason is all about speciation. This type of arsenic in this sort of compound, called an inorganic compound, will kill you. In lobsters, the arsenic is contained within molecules of an organic compound called arsenobutane, and instead of that being metabolized, it's excreted and you don't suffer from it. So it's extraordinarily important. What are the species and what concentrations are they? So the statement arsenic is poisonous is not always correct. depends upon which form, and indeed how much, what concentrations. It's about speciation. There's a lot to get your head around here, Aussie. You kidding, Prof? I'm still trying to get my head around the fact that if I put some sodium chloride into water, there's no sodium chloride there. I'm trying to figure out, is this not a magic trick? I understand it's not a magic trick, but the concept is one I'm not used to. Understood. Let these ideas stew and digest slowly. We'll be coming back to these ideas again and again and again because it's such an important idea in chemistry. For now, remember that the behaviour of solutions, for example, is governed not by what we put into the solution, but by what the species are that are in solution and what their concentrations are. Okay? Enough for now. See you next week. There are very, very important conceptual ideas here that Ozzy and I just talked about.